Is that?
That's right. That's good.
From University of Michigan, who's going to continue with Fibonacci sequences, dealing with point flips for the Fibonacci numbers and gaps. So I'm also hoping to see some Sesame Street or Disney characters.
Unfortunately, I might disappoint you.
But
I do have cookies, Chris.
So they ran away from you?
Yeah.
I see.
All right. Thank you for coming. Again, thanks for being here so early in the morning. Okay, so let's get started. So let's suppose that we're playing a game where we just flip a coin a couple of times. Say I flipped it n times and I've kind of recorded my answer. And given that, I would kind of like to ask two questions. The first question I would like to ask is, if I pick a string of heads at random from this sequence that I've kind of written down, this random sequence of heads and tails, but if I pick a string of heads at random, for instance, this string of heads here or a string of heads there, how long will it be? And the second question I'd like to ask...
Be careful, watch the lines there.
Okay. The second question I'd like to ask is, how long would I expect the longest run of heads to be? And so this is a very probabilistic question. You could probably be asked this in an intro course to probability, or maybe even high school. And so the question is, can we kind of generalize this sort of question? And one way that we could generalize it is by saying coin flips are really analogous to a random string of zeros and ones. For instance, my heads and tails could be translated into binary. And the question is...
Ignore it.
No.
So, if instead of taking a random binary string of length n, suppose we take a random binary string with an added condition. So suppose we take random binary strings with the condition that no two ones are adjacent. Well, now if I look at the longest string of ones in a row, it's not very interesting. But if I look at the longest string of zeros in a row, it might be a little bit more interesting, and you'd be wondering what would happen if we did this sort of thing. So fixing one random string, taking binary strings of length n with no ones adjacent, and how long will a random run of zeros within that string be? Or if I just pick an arbitrary string of length n, how long will I expect the longest run of zeros to be in that string? Okay. So what does this kind of have to do with difference equations or recurrent relations? Well, the first thing that we notice is there's a bijection between numbers in the interval 2 to the n plus 1 and to the n plus 2 and binary strings of length n. And what I do is I just take the binary decomposition of a number and then I just cut off the first thing. I cut off the first digit. So I take 13, I write it as 1101, but you know, if my number is in the interval 2 to the n plus 1 and 2 to the n plus 2, there's always going to be a 1 in the first the first term of its binary decomposition, obviously. So if we want to get a random string, then we'll cut off the first digit. And it turns out we can do something similar for the case where we have non-adjacent zeros and ones. So suppose we take a random binary string now and there's no ones adjacent. Well, in this case we have something that's known as Zeckendorf's theorem, which states that every positive integer can be uniquely written as a sum of non-consecutive Fibonacci numbers. And the way you would do this is you go and you take an integer and you subtract off the largest Fibonacci number from it, and then subtract off the next one, and so on and so forth. And for instance, 2014 can be written as F16 plus F13 plus F8, F4 plus F1. And notice we're starting our Fibonacci numbers a little bit strangely here. We're starting with a 1 instead of with a 1 and then a 2 instead of a 1 and then a 1. But it's really kind of the same thing. And so we can write 2014 in base Fibonacci. And so we can do a similar sort of thing where to our binary decomposition. And in general, if we take an arbitrary linearly recursive sequence and we make sure that all of our coefficients are non-negative, there's in fact a general way of constructing a unique decomposition for integers in the interval hn to hn plus 1. And then there's a way of defining kind of a sequence that corresponds, a notion of legality which corresponds to non-adjacency in the Fibonacci case, which will allow us to kind of write every integer in hn to hn plus 1 uniquely as a sum. Okay. So that kind of gives us a connection between these probability questions and questions about Zeckendorf decompositions, or decompositions of integers. And so statistics about coin flips are kind of related to binary decompositions. Random binary strings of non-adjacent ones are related to Fibonacci numbers. And these probabilistic systems are actually kind of governed by our linear recurrence. And that's the connection there. Okay, so what we've been studying is we studied statistics related to Zeckendorf decompositions. And here are some classical results. The first result is known as the Lukirka-Gross theorem, which is the first question you might ask is, given a Zeckendorf decomposition, a natural statistic is what are the number of summands that you might have to use decomposing a number in the interval fn to fn plus 1. And it turns out that the answer is n over phi squared plus 1, where phi is the golden mean or the eigenvalue associated to the Fibonacci recurrence relation. And further, and this was worked by people from Small, including Professor Miller, was that as n goes to infinity, the distribution of the number of summands in the Zeckendorf decomposition is normal. Alright, so now if we're asking questions about the longest run of heads, then we kind of need a notion of a gap between summands. So suppose you have a number, and it's written in terms of our sequence as a sum. Then we define the gaps between summands to be just the differences between the indices of the summands. So for instance, for this number, h1 plus h8 plus h18, the gaps between summands are 7 to 10. Okay, so the first question I was asking was a question about the average length of these gaps. So if I let p and k be the probability that a gap for decomposition in hn to hn plus 1 is the length k, a question you might ask is, what happens to that what is that probability as n goes to infinity? And a slightly more sophisticated question, which kind of corresponds to fixing a single number, which corresponds to fixing a single string, is if you fix a single number in the interval hn plus 1 to hn, I can kind of associate a probability measure to it by just picking a gap at random and looking how long that is. And that is what its individual gap measure is saying. And the question is, what is the behavior of kind of an arbitrary kind of random string as it goes through there? And so that was the first question I was asking. And the second question that I was asking translates very nicely into the longest gap, or the max of all the gap lengths of x. So the longest gap is just the max of all the gap lengths. For instance, for this number x, the longest gap is 12. So how does the distribution, how does the probability distribution of the longest gap behave as n goes to infinity? And this is a direct analog of the longest run heads. Alright, so let's look at some previous results. So Small 2011 did some work with just base B decompositions, which corresponds to throwing a die. And we also have this very nice theorem from Small 2011, which states that for Zeckendorf decompositions, remember this P of k, this is the probability of having a gap of length k. Well, P of k is 1 over phi to the k, or k greater than or equal to 2. And there's also a theorem about the individual gap measures, which states the individual gap measures. If you pick an arbitrary string from fn to fn plus 1, if it behaves, and you pick a random gap from that string, it behaves very closely to just picking a random gap from any string. Alright, and so kind of the new results that we have are for arbitrary recurrence relations. So if you have a recurrence relation where all of the coefficients are at least 1, then the limiting probability measure is given by a formula in terms of the eigenvalues of the recurrence. So lambda 1 here is the largest eigenvalue associated to a recurrence relation. And it's also a theorem that the individual gap measures tend to converge over time. So how would you get something like this? Well, essentially, it boils down to a fair number of combinatorics. So if you look at kind of the Fibonacci numbers again, LongesetGap gives us a lot of information on how many summands there are, and we can use that to kind of help us actually find out. We can use that to help us do our combinatorics and actually find out what the limiting probability is. So I'm just going to skim through this because I don't actually have that much time. But we do some combinatorics and we kind of count how many gaps there can be, and eventually we get to kind of a point where we have to, where it becomes very helpful to advantageous to use LongesetGap to replace the number of summands by the average, and we can do that using normality, and that's essentially how you get that sort of result. Now for the longest gap, the story is slightly different. So this is actually what happens for the longest gap. So if you let lambda 1 be the largest eigenvalue of the recurrence again, we could find the mean and the variance of the longest gap for most recurrences. And by most what we mean is for all recurrences except certain ones that the condition is essentially a condition on the coefficients of a polynomial in the coefficient. We want a polynomial in the coefficients of the recurrence not to have multiple roots, because that kind of screws up with kind of technical details later in the analysis. So it turns out that the mean of the longest gap grows logarithmically. This k is just a constant that's a polynomial and lambda 1. And what's nice is that we also have this Euler-Mascheroni constant that kind of pops up out of the analysis, and a -1/2. And so if you were kind of wondering what the answer was to the coin flip question from earlier, it turns out that coin flips, the mean of the longest run of heads in a coin flip grows logarithmically. And the other very interesting thing is that the variance is finite. So even though the mean is growing logarithmically, the variance of the longest run of heads is going to be finite. And so what that tells us is that if, for instance, I had potentially made up so I actually didn't flip a coin when I wrote down that sequence from before. And you can probably tell that because the longest run of heads that you saw there was not actually that close to what the longest run of heads is for an arbitrary, if I had actually chosen that sequence randomly. And so that's something that this might be useful for. Alright, so how do we go about proving something like this? Well, the first thing that we do is we find a generating function for the number of numbers in the interval hn to hn plus 1 with a longest gap less than f. And once we have this generating function, we can actually find the cumulative distribution function for the longest gap very easily from that. And then once we have the cumulative distribution function, we can apply some standard techniques to smooth out our sums and turn them into integrals, and then actually calculate our mean and variance. So for the Fibonacci numbers, our generating function will actually be this function here. Well, you'll notice that this 1 minus x squared looks a lot like x squared minus x minus 1. And so this will allow us to show that asymptotically the cumulative distribution function of the longest gap in Fibonacci numbers looks about like this. It's doubly exponential, which tells us that it's very tightly concentrated about the mean, which gives us the finite variance that we saw before. Alright, so how do we get this generating function? Well, remember, so the first thing, remember we want to find the number of numbers with the longest gap less than f. So if we just fix a k, and we only look at m and fn to fn plus 1 that have k summands in their Fibonacci decomposition, then we can actually find right away that the number of summands with the number of m with k summands and longest gap less than f is equal to the coefficient of x to the n in this expression. And so why is it this nth coefficient? Well, if I write m in terms of exactly k summands, the gaps uniquely identify which m I'm talking about in the interval. I'm sorry, this n here should be a k. these gap lengths uniquely identify an M because of Zeckendorf theorem. And we know that the sum of the number of gaps is less than or equal to n, each gap is greater than or equal to 2, and each gap has to be less than f by assumption, because that's what we're counting. And if we sum, and so if we sum over the total number of m in the interval fn to fn plus 1 with longest gap less than f, yes. So this allows us to condition on k, and unfortunately I think I'm missing a bit of a slide here, but to get rid of our conditioning on k, what we do is we sum over all k, and that allows us to sum over all k, we get our geometric series here, and we can evaluate it to be this generating function. And so, once we have a generating function, essentially the long-term behavior of this generating function is governed by the roots of this polynomial, 1 minus x squared, minus x squared, plus x df. And if we know kind of what the roots of this polynomial are doing, we can take a partial fraction expansion and thereby kind of get information on the cumulative distribution function. What's a little bit tricky is that the roots are kind of moving around a little bit because f is changing. But using Rouget's theorem, we can say that there's really only one root that matters, and that root actually converges to 1 over phi. And so that allows us to expand everything out and then apply our analytic techniques and actually get the mean and variance from that. All right, so that's how we go about our proof. We also have some numerical results related to the longest gap, and this was actually very useful for us because there were definitely some algebra errors for a little while. We were off by a factor. We were off by like plus or minus 1/2, and we didn't know whether it was a 1/2 or if it was the Euler-Mascheroni constant. So it was very nice to kind of have these numerics. So we have a pretty good agreement, or actually a really good agreement between our predictions and numerical results. So for the Fibonacci numbers, for the mean, we predicted if we sample 100 numbers from fn to fn plus 1 with n equals 1,000,000, we predicted 28.73, we observed 28.51 for the mean, 26.7 versus 22.44 for the variance. And sampling for recurrences that were not Fibonacci numbers is slightly more difficult because, well, it's slightly more difficult, but so we weren't able to kind of check quite as large numbers. But we also saw a very good agreement between experiment and prediction, and we have more numbers if we sample from 10 million instead of 1 million and 102,000 instead of 51,000. We also still see a nice agreement. And so we see a nice lining up between experiment and prediction. All right. So in terms of what we'd like to do in the future, one thing that would be nice is we have some conditions on which recurrences we can actually apply our techniques to. It turns out that most recurrences are subject to these techniques, but it would be nice to get all of them, and it kind of depends on. The algebra just gets more and more involved as you kind of loosen your restrictions more and more. So it would be nice to generalize our results to all sequences, and the other thing we would like to do is some other students of Miller have come up with different sort of decompositions associated. Different decompositions. It would be nice to look at the statistics of these. Thank you to Professor Miller for supporting me through small. Thanks to the NSF grants, and thank you for coming.
One more slide.
Yes, references.
Questions or comments for Phil? I'd like to ask a question about intervals. Do you ever consider shortening the intervals or breaking up into more intervals? Because I believe, if I'm not mistaken, that would give you more accuracy of what's going on.
The intervals? Or the intervals?
Yeah, intervals.
Yeah, so the reason why we chose the intervals that we chose is because they're kind of very natural. in terms of, well, yeah, so I guess I hadn't thought about that too much. Mostly because of the kind of recursive nature of how we're doing things, we're taking a number m and we're kind of finding a Zeckendorf decomposition. The way you do that is you subtract off the largest Fibonacci number beneath it. And so the nice thing about the interval fn to fn plus 1 is that I always know what the first number in this decomposition is. But it would be interesting to look at small intervals, and then maybe we get nicer behavior.
I mean, I've thought a little bit about trying to localize to a smaller scale than fn to fn plus 1. And what might happen is if your scale is, say, smaller by an exponent, you're going to just have a few of the summands changing. And you're essentially going to have your main block that's going to change you, and now you're trying to move square root of the distance. And so that's not going to change that many summands. So I think locally the function is going to be fairly constant. But that could change things like longest gap, because longest gap is a local phenomenon, not a global one.
Why?
Well, because I mean, for longest gap, it's on the order of log n. The number of terms you need is much smaller than the whole length of the interval. So if you focus on small subintervals, you might be able to see something interesting in longest gap.
I see. Interesting. Is there such thing as a shortest gap?
Yes.
It's not very interesting, though.
Why?
Well, that's just going to be the 2.
Oh, I got
And so, in fact, in previous work we showed that if you look at small gaps, it converges to geometric decay. And so, if your recurrence relation has only non-negative coefficients, then it's much easier, and you get geometric decay immediately. If your recurrence relation has 0 coefficients, it's geometric decay once the gap is longer than the length of the recurrence, and no student of mine really wanted to look at the algebra needed if it's shorter than the length of the recurrence. But it is doable with just a finite amount of tedious algebra.
I see. Neat. Okay, other questions or comments for Phil?
Have you ever thought of how this might be related to the longest common subsequence problem?
No, I actually don't know about that problem.
Well, it comes up in biology. I don't know if there's anybody in biology who can explain better. So if you think of 2 sequences of DNA and you want to see what's the longest common subsequence between the 2.
Okay.
You can think of that as zeros and ones. If you just say these 2 match, you get a 0. These 2 match, you get a 0. These 2 don't match, you get a 1.
Yep.
So you want to know what's the longest common subsequence. And a lot of times you could, 2 DNA strands end up having a lot of zeros and ones in a row if they match. Or a lot of times what happens is you have what's called an indel, where one ACT or G is deleted, which shifts everything by 1, and then makes a whole huge sequence of things that are off by 1. And if you can figure out where those indels are, you can usually line them up so that you get a long sequence of things that match with one thing that doesn't match in the middle. And so you have this sort of your setup where you have lots of zeros, 1, 1, lots of zeros, 1, 1. But then the problem is figuring out what's the longest common subsequence and what's the asymptotic sub.
That's very interesting.
So you might want to look up that.
I'd be interested in looking at that.
I mean, you could probably cast a lot of this maybe probabilistically and say,
Correct.
I have probability P that they align here. And now it's the same as just a biased coin. And so there's a really nice expository paper by Schilling on the length of the longest line of heads. And he goes through this for a fair coin, for biased coin. And so I think the answer would be known in this case. And it would just be, can we interpret that in terms of some kind of decomposition problem?
I haven't looked at 10 years ago maybe, and I know for a 50-50 coin it was known, but anything off of that wasn't.
I'll check. I think it's known. It's just no. They definitely know that they definitely know the longest gap. Yeah.
I think they do weighted. They know weighted points for sure.
Yes.
The reason I know a little bit about all the weighted points is because we were trying to use that to do. We're trying to use kind of their techniques to do our stuff, but
Right.
it wasn't really feasible.
Because their techniques assume independence, that each toss of the coin is independent of the previous. And there's a small dependence in these decompositions. Clearly if you have a summon, you don't have the next one. And so we couldn't quite cast it in the coin model. But it was a very useful framework. And our answer is actually extremely close to what you would get if you look at the recursive relation Gn is twice Gn minus 1. And that'd be the fair coin toss of just binary decompositions.
Interesting. Other questions or comments for Phil? Okay, let's thank Phil one more time.